Okay, hello everybody. The chapter that we're going to learn today is chapter 5, discounted cash flow valuation, but more likely it's called time value of money in the second part of it. So in this chapter, we would learn how to compute the present value and future value of multiple cash flows. So there are two types of multiple cash flows, multiple equal cash flows and multiple unequal cash flows. We will start with unequal cash flows and we'll move on to multiple equal cash flows. And these multiple equal cash flows are usually called annuities and perpetuities. So we will learn how to understand and compute annuities and perpetuities. And more precisely, we will learn how to explain the differences between ordinary annuities and annuities due. And we would also learn how interests are quoted, especially we will learn the difference between what's called the annual percentage return and also effective annual returns. And also we would, of course, we would continue to learn how to use the financial calculator for time value of money calculation. So the corresponding subchapters here would be 5.1, 5.2, and 5.3. Okay, so let's start from multiple unequal cash flows. And for here, we will start directly with an actual example. So the question asks, if you deposit $100 in 1 year, $200 in 2 years, and $300 in 3 years, then it's asking how much you would have in 3 years. So what's different from a previous class is we started with a lump sum single cash flow. But then right now with this example, we have multiple cash flows along the time period. So regularly you're given a certain amount of, you would have to just take into account a certain amount of money value. And then the particular thing here is that these amounts are different. So if you have different amounts along the way and you want to compute either the future value of them or the present value of them, how are you going to accommodate that? It is very simple. You will just have to treat them separately and then just combine the sum in the end. So what you see here is like how you would do with like just single lump sum cash flow. All right, so $100, let's suppose $100 you would have to deposit it. How much would that be in the end of the 30-year term? Okay, so you're going to treat them separately and we'll combine the future value in the end. So let's start with the first cash flow, which is $100 deposited in the end of the first year term. So that amount will have to sit in your bank account for 2 more years, right? So that's why you're going to treat the number of periods as 2, all right? And we'll try to compute that amount for the future in the end of the 3rd year, and it will be 114.49. Same thing for the second cash flow, which will be deposited in 2 years by the end of the 2nd year. So how long will it sit there in your bank account? 1 more year, right? So you will just have to figure out the time period by subtracting that particular number of year from the length of the total time period. All right, so that would be 1 in this case. So you just take 1 as your time period and just plug that in the original formula, and you would have 214 for the future value. And for the third cash flow, which is going to be deposited in the end of the 3rd period, then it wouldn't have any time period to collect interest. So it's just the original deposit amount itself. So it's just 300. So with all these future values, if you just add them all, then you will know that you will have 628.49 by the end of the 3rd-year period. So just the rule here is to treat them separately. And of course, you can do that separately on your calculator as well. And for all the calculator works, I'm going to shoot a separate video where you can watch how to input these numbers on your calculator. So the second exercise question, suppose you plan to deposit $100 into an account in 1 year and $300 into an account in 3 years. How much will that be in the account in 5 years if the interest rate is 8%? So what it's asking is, you are going to deposit $100 in the end of the 1st year, and you're going to skip the 2nd year, so 0 in 2nd year. In the 3rd year, you're going to deposit $300 more. And the difference here from the first one is that you're gonna check out the amount in the end of the fifth year. So basically your time period, the length of the time period is 5 years instead of 3 years, which was the case for the first example. All right, so how much will that be in 5 years? And of course, once again, you're going to treat them separately. So $100 being deposited and staying there for another 4 years, right? 5 minus 1 would be 4. So it's going to sit there for 4 additional years. And finally, you want to check out the amount in the end of the 5th year. So how much would that be? So $100 being deposited at 8% for 4 more years, and you will have 136.05 by the end of the 5th year. Same thing for the amount that you'll deposit in the 3rd year. So remember that this is being skipped, so you can just skip this as well. And then let's just move on to the 3rd year, where you will deposit $300. And if you deposit it in the 3rd year, it's going to sit there for 2 additional years. So 5 minus 3 would be 2. So it's going to sit there for 2 additional years. That's why the length of the time period will have to be 2 in this case. You just punch that in on the original formula, and it means that by the end of the 5th year, this will grow to be 349.92. So you have these separate future value amounts added together, and that would be equal to 485.97. And of course, you can do the same thing on your calculator, which will result in the same value. So if you want to put that into one general formula, once again, you're going to treat all these cash flows separately. So each part here would represent the future value of separate cash flows. And here you should note that the time period, once again, is the total time period, the entire length of time period minus wherever, which specific period that cash flow is located in. For example, if it was located in the 1st year, then you will just have the time period as the total period minus 1. So it will just continue to happen, and you just sum them all together, which will be the sum of the future values. Now then, why don't we move on to the unequal cash flows present value. So here we're going to just reverse the order here, and with all the cash flows, the different cash flows that we have throughout the time period, we want to figure out how much it would be worth in today's value. So let's start with another example. So you're offered an investment that will pay you $200 in year 1, $400 in year 2, $600 in year 3, and $800 in 4th year. So with interest rate being 12%, what would be its equivalent value in today's money? So if this is some kind of investment program or an investment that will pay you with this schedule, how much are you willing to pay for this, which is the equivalent value in today's money? That is asking for present value. And here with that, you're going to treat that separately once again. So you want to figure out the present value of each cash flow. $200 in today's value, $400 in 2 years in today's value, $600 the same thing, $800 the same thing, and finally you would like to add them all together in the end. So it's just basically the same thing that you did with the future value, except that you are using a different formula. You're dividing it by 1 plus the interest rate to the time period instead of multiplying it. And another different thing is, because this is trying to figure out the time period between year 0 and that specific time period, you will just have the same number as the year number as your time period, and that will just suffice. Okay. And of course, with the calculator, you can do it the same way as well. So just using the calculator, you'll treat them separately, treat all the cash flow separately, figure out the present value and sum them all together as we did with single cash flow present value. But there's actually one sophisticated function that you could use on your calculator, which is the cash flow or CF function. And this one, since it is very important, I really want you to take a look at this section in the video, in the separate video that I'm going to shoot, which is the calculator exercise part. And I really want you to pay extra attention there, because this is a little bit, this involves more steps that you would usually take. Okay, so make sure you check out this section in your video, in the calculator video. Okay, for the second exercise, which looks very similar, let's suppose you're considering an investment that will pay you $1,000 in year 1, $2,000 in year 2, and $3,000 in year 3, and interest rate is 10%. Then how much are you willing to pay, or what is the present value of this investment? Then of course you can just treat that separately as you would with a calculator. I'm just omitting the time frame and the calculator work here because it is just basically the same thing. But my recommendation once again is for you to check out all these steps on your on the calculator video. Okay, so if you wanted to just present it in one generic formula, then once again, you're in terms of the formula, the only way you can do it is just treating them separately and just combining them all together in the end. Now let's move on to multiple cash flows with equal cash payments. There are two types of multiple equal cash flows. One is annuity and the other one is perpetuity. So the similarities and differences between annuities and perpetuities would be both of them are, as the name suggests, both of them would involve equal and regular cash payments. And the difference between the two would be one has a finite time schedule and the other one has perpetual, as the name suggests, perpetual time period. If you try to present these cash flows in a time period, the time period is fixed for the annuity and the time period is with infinity if it were a perpetuity. And there are two types of annuities. One is an ordinary annuity and the other one is annuity due. And for ordinary annuities, the payments would be made at the end of each period, whereas annuity dues would involve payments at the beginning of each period. And also, for the last thing, perpetuity, once again, the definition is infinite series of equal and regular payments. So let's take a look at ordinary annuities and annuities due in depth. So first of all, the future value of an ordinary annuity. We are trying to compute the future value of regularly repeated cash flows of an equal amount, with the payments being made at the end of each period. For example, so one here, this tick mark would indicate the end of the first period. Second, the payments being made at the end of the second period, and so on until the end of this finite time schedule. And this payment, if these are made like this, and if we wanted to figure out the future value of it, that would be the future value of an ordinary annuity. Present value would be the opposite way. So all these payments being made at the end, if we want to figure out how much it would be in today's value, that will be the present value. And another type of problem that we can think of is payment. Okay, so until now we only were focused on how to get the future value or present value of a cash flow schedule. But right now, because there is one more important variable, we sometimes are asked to get that value. So this present value, if we were given the all these payments, which are supposed to be the same amounts, if we are given the present value and future value, then we can also figure out how much like equal payments would make these present value and or future value possible. So that's another type of problem you should expect from this this type of cash flow schedule. So let's suppose you wanted to compute the problem with a formula. Then the formula, there is actually one formula that will make it possible for you to compute the future value or present value. So it's just given in this red bold formula. So you might as well, if you want to just solve the problem manually, you can just leverage the formula that was provided in this slide. So there are 4 exercises that will help you practice a problem related to ordinary annuity, both for future value and present value. So let's suppose you're asked to compute the present value of a 4-year annuity when the cash flow, the regular cash flow amount is $100, and it will be paid 1 year from today. So note that whenever you say that the first payment is made like 1 year from today or 1 month from today, indicating that it's being paid out at the end of each period, then this is an ordinary annuity. And it says the discount rate is 9%. So one way to compute that would be to use the formula that was presented in the earlier slide, right? So you just plug in the number and it will give you the answer. So you can just leverage that formula. However, once again, more simplified way of doing it would be using the calculator. So all these keys that you can punch in is keys that you can punch in are provided here, but you can also watch the video with calculator work. And a similar problem for exercise 2. So let's suppose you can afford $632 a month with an interest rate being 12%. And here is an important thing. So most likely you will have a different compounding period, and it says it's monthly compounding for 4 years. So you're able to make a payment, monthly payment amounting to $632 per month with an interest rate of 12%, monthly compounding for 4 years. And if that were the case, how much can you borrow? What is like the amount of loan that you can get with this information? So with this, you will have to make some kind of adjustment here in terms of the interest rate. Your annual interest rate was 12%. However, given that the compounding period is compounding frequency is monthly, and also you are given the monthly payment amount, you will have to adjust this interest rate into the monthly rate as well. So in terms of the formula, so this is the formula that you will use, and for interest rate in this place, you will have to use 12% divided by 2, which is 1% instead of 12%. Why? Because we're taking into account the monthly payment period and also a monthly compounding frequency. And also in terms of the number of period, you will have to use 48 months because it's 12 months. There are 12 months and you have 4 years. So 12 times 4 is 48 months. So you're going to use 48 as the number of periods. So whenever you have different compounding frequencies, as you did with simple, like single cash flow, you would have to adjust the interest rate and the number of periods as well. And you will get the answer here. And same thing with the calculator. You will not use 12% or 4 years, but in terms of the number of periods, you will have to use 48. And in terms of the interest rate, you will have to 1. So this is the adjustment that you will need to make and use the calculator as shown here. Exercise 3, once again, a very similar problem, except that you are asked about the future value. So depositing $50 a month with an annual rate of 9%, but the monthly compounding frequency is monthly. So once again, you'll have to adjust the interest rate and the number of periods. And it's asking you how much you will have in 35 years. So in terms of the formula, you will need to input the interest rate as 9% divided by 12. So every month you're given a monthly rate of 0.75% or 0.0075. That should be what you're using for the interest rate. And also in terms of the number of period, instead of using 35 years, you'll have to multiply that by 12 so that you will have 420 months here. So 420 would be your number of periods, 0.75 should be your interest rate, and so on. You will have a different amount for your, this is the amount you should have here for future value. Now, exercise 4 is supposed to be more like a comprehensive problem that is just encompassing everything that you need to know about not only just the time value of money, but it's kind of taking into advantage a lot of factors related to mortgage. So you might as well pay extra attention here as well. And a more detailed approach can be found in the video with calculators. But once again, I'm trying to explain this as detailed as possible here. You're trying to buy a house and you have $20,000 for a down payment and closing costs. So what that means is out of this $20,000, you're gonna spend a portion of it for down payment and the other part of it for closing costs. So it's not just for down payment. You will have to pay closing costs out of this as well. And closing costs right now are estimated to be like 4% of the loan value. So in a sense, if you wanted to figure out the closing costs, you will have to first know the loan value. Right? But right now you don't know the loan value yet, right? You have an annual salary of $36,000. So that means $36,000 every year indicates every month you will be getting $3,000. Okay, that's your monthly payment. And the bank is willing to allow your monthly mortgage payment to be equal to 28% of your monthly income. So out of your monthly income of $3,000, only 28% can be counted towards your mortgage payment. If it goes higher than that, your bank will not allow it because there is something called the DTI or debt to income ratio that the bank will have to keep up with. And the DTI for your bank and for your situation, it's 28%. So even though you're making $3,000 every month, that cannot the entire monthly salary cannot be paid towards your mortgage payment. Only a portion, which is 28% of it, will be counted towards your mortgage payment. Interest rate on the loan is 6% per year, monthly compounding. And with monthly compounding, that is the norm in the US, right? So mortgage is paid every month. So what that means is you will have to take into account the monthly rate instead of the annual rate. And you are using a 30-year fixed rate loan here as well. So with all this background information, the first question asks how much money will the bank loan you, all right? So you will first need to figure out how much you can pay towards your mortgage every month. So to do so, you will have to use $3,000 in the mortgage payment, 28% out of it. So every month, the maximum amount you can pay for your bank loan is $840. So you know the payment amount, you know the interest rate, you know the time period. So you would have to figure out the bank loan just taking into account all these variables. And whenever you're asked this loan problem, are you asked a present value or future value? And a lot of people are kind of confused with that, but the answer is always present value. You are always taking the loan right now. You need the money right now. That's why you're taking the loan. So whenever you're asked about the loan amount, then you will automatically have to compute the present value. So bank loan will be the present value of the mortgage payment. So with that, if you use the formula, once again, in place of the interest rate, you're using the monthly rate, which is 6% divided by 12. And in terms of the number of periods, this would be 30 times 12, which is 360. You just plug in the numbers in the formula, and it says, according to the formula, you should have 140,105. Okay, so the maximum amount of money that you can borrow from the bank is about 150,000, given your financial situation. So 150, is it the same as the price that you can offer for? No. How much can you offer for the house then? Then you will have to just take into account additional information here. Remember how you had you already had in your pocket 200,000, was it 20,000, right? 20,000. So you'll have to keep that in mind as well. But part of it has to be paid for your closing costs. And since you know the loan value now, you have to multiply that by 4%, which gives you the closing costs. Closing cost right now is $5,604, according to the formula. And the down payment, if that were the case, down payment is like the remaining part of the money that you have right now. So 20,000 was the money that you had. Out of that, you're paying out 5,604 as closing costs. So the remaining would be 14,396. So that can be paid towards your house. So in addition to the loan, if you use this down payment amount, so 140,105, which is the answer from Q1, and you add the down payment, then you should have 154,501. This is what you can pay for your house. So the maximum amount of house that you can purchase at the moment is 154,501. The other type of annuity is annuity due, and the only difference here is that the payments are made at the beginning of each period. So as you can see, if the payment period is different, then the present value and the future value will be different from the case when the payments are being made at the end of the period. For annuity dues, for example, for future value, all the payments are being made one period earlier. So you would have more time to accrue interest to the last minute of the time period. So in a sense, future value will have to be higher compared to an ordinary annuity. And also in terms of the present value, once again, we are trying to figure out the present value for all the payments that are paid at the beginning of each period. So compared to ordinary annuities, payments are being one period earlier. And so that means, if you just think about the value of $1 that is paid right away and $1 that is being paid out one period later, it's always $1 paid out right now is always worth more than $1 paid out later. So all these payments will be worth more, meaning that the present value will be different for an annuity due compared to an ordinary annuity, and also higher. And another type of problem that you would come across for an annuity due is, once again, you would be asked to compute the payment when present value and or the future value are given. So here are the general formulas that you can use for annuity due calculation, both for future value and present value. And if you wanted to use it for actual examples, here are the exercises. So first, this is actually the same problem with the first exercise from the ordinary annuity, except that the payments are being made in the beginning. So if you wanted to differentiate it, you just want to pay attention to this part right here. So it's asking you about the present value of a 4-year annuity of $100 per year, and the payments are being made. The first payment is being made today, meaning that it will always start at the beginning. And if the discount rate is 9%, you could calculate the present value by using the formula from the earlier slide. Now, if you wanted to use the calculator, there is actually one extra step that you need to take related to the time period, the period that the payments are being made. So there are some changes you need to make regarding changing from end to beginning. So this is indicating the payments are being made at the end, and also if you need to take extra steps to make it change it to beginning. And this step is actually better explained in a separate video, not only the video with calculator for exercises, but also if you just go to the basic calculator tutorial, you may find it at the last part as well. Okay, and another exercise here. So let's say you just won a contest and you will receive $10,000 a month for 20 years starting today. So remember how whenever the problem has a phrase like starting today, the first payment is being made today, that always kind of just alludes that this is an annuity due problem. So with an annuity due problem, if you use the formula from earlier slides, then it will allow you to compute the present value of this annuity. And also note that since it's a monthly payment and monthly compounding, you will need to use a monthly interest rate rather than an annual interest rate. And also for the time period is not 20 years, but 20 times 12, which is 240 months. Okay, let's wrap up the annuity discussion here. So if you wanted to compare the ordinary annuity and annuity due, as suggested before, you might wonder what's the difference. And if you wanted to take a look at the difference more visually, so annuity dues for like corresponding payments always the payment would be made before for annuity due, but ordinary annuity, the payments come always like one period later. So if you just wanted to compare the values in terms of the amount of values, if we just focus on the present value, the payments are always being made earlier, one period earlier for annuity due. So remember how we wanted to compare $1 today and $1 tomorrow. It's always worth more if it was paid today. The sooner the higher. So if we wanted to compare the amount for annuity due and ordinary annuity, annuity dues will always have a higher present value compared to ordinary annuities. And that will be the same for future values. If you compare the corresponding payments, annuity dues will be paid out earlier, indicating that it has more period to accrue interest. That's why annuity dues will always yield a higher future value as well. The last topic for multiple equal cash flows, which is perpetuity. Perpetuity is all these equal payments being made forever, okay, for an infinite period of time. If that were the case, there is no calculator keys that you can use. However, there is one very simple formula that you can use. So present value in this case, of course, there is no future value because there is an infinite period of time. But for the present value, you can just use payment divided by the interest rate, and that will compute the perpetuity for you. So what is the present value of a stock that promises to pay dividends of $100 forever if the discount rate is 9%? Then the formula would be payment divided by interest rate, which is 1111.11. The last topic is the interest rate. So before we start, there is a question that I would like to ask. So which of the following, between the two, which of the following will yield a higher return in fact? So $50 invested at 12% for 3 years, and the compounding frequency is semi-annual. And the other one is $50 invested at a different interest rate, which is 12.3% for the same 3 years, but here the compounding frequency is annual. So here it's just hard to make a decision because it's not an apple-to-apple comparison. One has a frequency of semi-annual compounding and the other one has an annual compounding frequency. And also the interest rates are different. So for an apple-to-apple comparison, we need to standardize these interest rates. We need to know the effective rate of return for these two cases. So we would like to have an understanding of what an effective rate of return is. So there are two types of interest rates that you will come across. One is effective annual rate of return, or sometimes effective annual return itself. It's EAR. And the other one is annual percentage return, or annual percentage rate. Effective annual rate of return would be the interest rate expressed as if it were compounded once a year. So a lot of times you will see a different compounding frequency, and there is a conversion that you need to make to express it in terms of an annual compounding. If so, that will be called the effective annual rate of return. So why do we need that? We need that to compare two alternative investments with different compounding periods. So in a sense, we would like to have a standardized return, which is why we need an effective annual rate of return. Annual percentage rate of return, on the other hand, would be the annual rate quoted by law, or whatever periodic rate, for example. So let's suppose every month you're given like 1%, then you will just multiply that by the number of periods or number of frequencies. Then that will be APR. Most likely what is just presented on a contract or a statement, which is like a normative return, that is the annual percentage rate of return. So with these two interest rates, if you wanted to kind of make a conversion between one to the other, there is a formula that you can use, which is EAR being the same as 1 plus annual percentage rate of return divided by M. Here, if you recall chapter 4, M would stand for the frequency. For example, semi-annual 2, quarterly 4, monthly 12, and so on. Okay, so you divide it by the frequency, take it to the power of the frequency itself, okay, 2, 4, or 12, and that will be taken as your power, and subtract 1 in the end. That will give you the effective annual return. So you can just go between one or the other by either using this formula, or maybe if you're given the effective annual return, you can just rearrange this equation to compute for the APR. However, in many cases, APR, as I told you, these are the returns that you will find on your statement or a contract. So these are the normative returns. So from here, most likely you will be asked to compute the effective annual return. So let's take a look at an example. So suppose you invest $50 for 3 years at 12% compounded semi-annually. So 12% here, this is supposedly the annual percentage return, which is APR. So with APR, if this was compounded semi-annually, you're asked what the amount it would be in 3 years. So if your investment, if you take a look at this future value formula, $50 growing at 12% APR compounded semi-annually. So you will have to divide it by 2 and then take it to the power of the frequency times 3. So this is just the usual future value formula with different frequencies, which you saw in chapter 4. Okay, and if that were the case, this amount will grow to be 70.93 in 3 years. So from here, if we wanted to figure out the effective annual rate of return, what that means is if we were just applying this one single formula with just annual number of years, then which effective annual rate will give us the same result? That is the definition of effective annual return. And if you just figure it out this way, then you will find out that the effective annual return is 12.36%. So this is just a long way to get there. However, if we were just applying the formula that we learned before, it will yield us the same result. So what does it mean? If we invested at 12%, which is compounded semi-annually, then this would give us the same result as investing at 12.36% compounded annually. So without any different compounding frequency, if you were just going in a very smooth and normal way, annual compounding, 12.36% would give us the same result. That is the definition of effective annual return. So once again here for A, $50 invested in 12% for 3 years compounded semi-annually would be the same thing as $50. So if we just wanted to make it the same as just an annual compounding instead of 12%, you can just use 12.36% for 3 years compounded annually. That would give us the same result. So what that indicates is you're just, for an apple-to-apple comparison, 12.36 versus 12.3. So what would give us a higher return? It would be A. So this is the last topic to be covered for chapter 5. So for the remaining part of this lecture note, I'm going to shoot a different video related to the comprehensive exercise. That would be related to, it will be encompassing everything that we learned throughout this throughout the time value of money section, which is chapter 4 and 5. So you might as well just pay extra attention to that part as well.